Bismillahirrahmanirrahim. Assalamu alaikum students. This is Hamza Noor from Aero Education Network. And in today's video, I'm going to solve some more questions from the topic functions, particularly domain and range of functions and domain and range of complex functions and inverse functions as well. Overall, we are having a practice of functions topic, pure mathematics 1, AS level maths 9709 Cambridge. In my previous video, I solved question number 30, 32 and 33 from the handout. Now we have question number 34, which is May-June 2018, paper 1, variant 1, question number 9. So here we have functions f and g, which are defined for x can take any real values, meaning there is no restriction on the domain of both of these functions. X belongs to the set of real numbers, means x can take any real values. By fx is a linear function, which is half x minus 2, and gx is basically a quadratic function, which is 4 plus x minus half x square. And the requirement of part 1 is to find the points of intersection of the graphs of y is equals to fx and y is equals to gx. This part is worth 3 marks. We need to find the complete coordinates, the points of intersection, meaning the coordinates in the form of x comma y. All right. So what we are going to do, first thing first, in order to find the points of intersection, we are going to equate the fx and gx functions with each other. So fx is equals to gx, meaning half x minus 2 is equals to 4 plus x minus half x square. So we are going to collect all of the terms on one side. So half x square plus half x minus 2 minus 4, and this whole thing is equal to 0. And now we are going to simplify the terms. So half x square and then half x minus x will give you minus half x, and then minus 2 minus 4 is minus 6, and this whole thing is equals to 0. So far we have achieved this thing. So in order to make this quadratic equation more simpler, what we can do is multiply 2 on both sides. Okay, so x square minus x minus 12 is equals to 0. And now we are going to solve this quadratic equation. So if we factorize, so 4 times 3 is 12, and after subtraction we need to get minus 1 in between. So x square plus 3x minus 4x minus 12 is equals to 0, meaning taking x as common multiplied by x plus 3, taking minus 4 as common multiplied by x plus 3, and this whole thing is equal to 0. So therefore the fully factorized form is x plus 3 multiplied by x minus 4 is equal to 0. So equating both of the factors with 0, when x plus 3 is equated with 0, so x is equal to minus 3. And similarly, when x minus 4 is equated with 0, so x is equal to 4. These are the x coordinates of the points of intersection. However, we need to find the complete points of intersection. We need to find the corresponding values of y as well. And for that purpose, either you can substitute these values into the fx function or in the gx function. So fx is simply a linear function, so I'm going to substitute it into the fx function. So value of f minus 3 will be half times minus 3 minus 2, and the value of f4 will be half times 4 and then minus 2. So the value of f minus 3 is basically minus 3.5, and the value of f4 is basically 0. So therefore, the points of intersection are 4, 0 and minus 3, minus 3.5. This is supposed to be our answer to part 1. All right. These are the points of intersection of the graphs of fx and gx. 4, 0 and minus 3, minus 3.5. So after this, we have part 2, which says that we need to solve this inequality, find the set of values of x for which fx is greater than gx. So here I'm going to solve part 2. So we need to solve this inequality fx is greater than gx, which essentially means that fx minus gx is greater than 0. And what we have achieved in part 1 is that the most simplified expression and then the factorized expression for fx minus gx, which you can see over here, which is x plus 3 times x minus 4. So simply in place of fx minus gx, I'm going to write x plus 3 multiplied by x minus 4. Okay, and this whole thing is greater than 0. And now we need to only solve this quadratic inequality. So when x plus 3 is equated with 0, so x is equals to minus 3. And when x minus 4 is equated with 0, so x is equals to 4. These are the critical values of x now, because we are solving the quadratic inequality over here. These are the critical values of x. So I'm going to sketch a quadratic graph. So in order to solve the quadratic inequality, always helpful to sketch the graph. So as we can see that the coefficient of x square is positive. So the least standing quadratic graph, the least standing point quadratic graph, meaning U-shaped quadratic graph. Okay, one value is minus 3 and the other one is 4. And since the inequality is that greater than 0, so the region which is bounded by the quadratic graph in the x-axis, or I can say the part of the quadratic graph which is above the x-axis. So according to our shading and observation, we can say that x is either below minus 3, comma x is greater than 4. This is basically the quadratic inequality solution. X is below minus 3, comma x is greater than 4. All right. So in this way, we have attempted part 2. Most of the working was already done in part 1, and we have just used the result of part 1 which we obtained over here, that is x plus 3 multiplied by x minus 4, which we obtained, you know, after uh, after subtracting the gx function from the fx function. All right. So in this way, we have attempted part 2. All right, so now let's move on to part 3, which says that find an expression for fgx and reduce the range of fg. So I'm going to bring this question on the next page so we can have more space. So what we need to do, we need to find an expression for fgx first. Okay, so fx is basically a linear function. Fx is equals to half x minus 2. So now the input of the fx function is gx function itself. So in place of x, we are going to substitute gx. So half times gx and then minus 2, which essentially means half is completely multiplied by 4 plus x minus half x square and then minus 2. And now in the next step, we are going to expand and simplify. So half times 4 is basically 2, and then plus half times x, which is half x, and then minus 1 over 4 into x square, and then minus 2. So as we can see that this 2 and minus 2 are cancelled out. Okay, so therefore f of gx function is supposed to be half x minus 1 over 4 times x square. All right, this is basically the composite function expression for f of gx. And now we need to reduce the range of fg. So this is basically an expanded form, a general form of the quadratic expression. So if you compare it with the form of ax square plus bx plus c, so a is equals to minus 1 over 4, b is equals to half, and c is equals to 0. So what I can do, I can convert it into a completing square form. So the formula which I use for converting the expanded form into a completing square form is a multiplied by x plus b over 2a whole squared plus 4ac minus b square over 4a. So I can say that minus 1 over 4 multiplied by x plus half divided by 2 times minus 1 over 4, and then this is whole squared, and then plus 4 times minus 1 over 4 times 0 minus half squared, and then completely divided by 4 times minus 1 over 4. All right, so I can say that minus 1 over 4 outside, and then inside the bracket, 0.5 divided by 2 times minus 0.25. So inside the bracket x minus 1, and this is whole squared, and then we are going to evaluate this thing, 4ac minus b square over 4a. So the value of 4ac minus b square divided by 4 times a, it is supposed to be 1 over 4. So positive 1 over 4. So therefore we can say that, the turning point of the quadratic graph when x minus 1 is equated with 0, so x is equals to 1, and the y coordinate is positive 1 over 4. And since we can see that the coefficient of x square, meaning a, is negative, so this means that turning point is maximum. And the graph passes through the origin, because when input of the function is x is equals to 0, so output is also equal to 0. So according to all of this information, I'm going to make a sketch of this quadratic graph, because in order to find the range of any function, always helpful to sketch the graph. So the graph will pass to the origin, okay, and it will have a maximum turning point. All right. So the maximum turning point is, the x coordinate is 1 and y coordinate is basically 1 over 4. So therefore we can say that the range of this composite function f of gx, the range of this composite function f of gx is that f of gx is less than or equals to 1 over 4. This is supposed to be our answer. F of gx is less than or equals to 1 over 4. All right. So in this way, we have found the range of the composite function over here by sketching the graph of the f of gx function. An alternative way is that you can differentiate the composite function over here, since this is a quadratic function. So in order to, uh, find the turning point of the quadratic graph, you can find the dy over dx function and equate it with 0. So that's also fine. Okay, so let's say equation of the curve is basically y is equals to half x minus 1 over 4 times x square. So I'm going to find the dy over dx function. So when half x is differentiated, this becomes half and then minus 2 over 4 times x, meaning dy over dx is a linear expression which is half minus half x. Okay, so dy over dx is equated with 0. So half will be equals to half x, meaning x will be equals to 1. This is basically the x coordinate of the stationary point. Okay, and the stationary point over here will be the turning point of the quadratic graph. So when x is equals to 1, we are going to see what is the output of the function. Okay, so half times 1 minus 1 over 4 times 1 square. So this is half minus 1 over 4, which is basically 1 over 4. This is the output of the function. Okay, output of the composite function when x is equals to 1. So this means 1 comma 1 over 4, 1 comma 1 over 4 is the maximum turning point of the quadratic graph. Why maximum? Because the coefficient of x square is negative. That's why. Okay, and after this you will sketch the graph in this way, and then you will tell the range of the function over here. So this was basically an alternative approach. All right, the alternative approach was to find the dy over dx function and equate it with 0. So in this way we have attempted this part 3. All right, so now let's move on to part 4. Part 4 says that the function h is defined by hx is equals to 4 plus x minus half x square for the domain x is greater than or equals to k. Part 4 says that find the smallest value of k for which h has an inverse. Okay, so basically in these type of questions, the domain of the quadratic graph is restricted from the x coordinate of the turning point. All right, so what we are going to do, we are going to convert this expanded form of the hx function into a completing square form, and we are going to uh, identify that what is the x coordinate of the turning point of the quadratic graph. So for this purpose, I'll bring the question again. on the next page. All right, so we have an expanded form for this hx function. Hx is equals to minus half x square plus x plus 4. So I'm going to convert this into a completing square form. So I'm going to use the same formula, a multiplied by x plus b over 2a whole squared plus 4ac minus b square over 4a. Alright, so a is minus half, b is 1, and c is 4. So minus half is completely multiplied by x plus 1 upon 2 times minus half. This is whole squared, and then plus 4 into minus half into 4, and then subtract 1 is squared, and then completely divided by 4 times minus half. So this means that minus half multiplied by what inside the bracket, 1 divided by 2 times minus half. This will give us minus 1. So inside the bracket x minus 1, this is whole squared, and now I'm going to evaluate the value of 4ac minus b square over 4a. So 4 times minus half times 4 minus 1 is squared, and then completely divided by 4 times minus half. So this is supposed to be 9 over 2. All right. So this essentially means that when x minus 1 is equated with 0, so x is equals to 1, and the y coordinate is equated with 9 over 2, meaning 1 comma 4.5 is basically, the turning point of the quadratic graph, which is the maximum turning point. Okay. So now the thing is that the x coordinate of the turning point is 1. So what we can see over here is that the maximum turning point of the quadratic graph is above the x-axis, meaning this is 1 comma 4.5, and the turning point is maximum since the coefficient of x square is minus half. So the domain for this hx function is that x is greater than or equals to k. Okay, so x coordinate of the turning point is 1. So if the domain is that x is greater than or equals to 1, therefore we are going to say that the inverse of this function is possible, and this is a one-to-one function. Okay, so as we can see that if we make horizontal lines over here, the graph will intersect at all places at one point, at exactly one point. So this means that this function passes the horizontal line test. Okay, so this means that the smallest value of k is basically equals to 1. Okay, and in order to give some more detailed explanation, let's say if the domain was like this, x is greater than or equals to 2. Okay, so let's see, when we put input of the function h as x is equals to 2, what is the output? So 4 plus 2 minus half times 2 is square. So the output is basically 4. Okay, so when input is 2, output is 4. So if I say that the graph is something like this for the domain x is greater than or equals to 2, okay, so still the inverse would be possible. However, this would not be the smallest value of k. Okay, the smallest value of k would be the x coordinate of the turning point of the quadratic graph. Okay, so if I say that hx function is sketched for the domain x is greater than or equals to 2, okay, so the inverse would be possible. Inverse would be possible. However, this 2 would not be the smallest value of k. We have a smaller value of k as compared to 2, which is basically 1. All right, so this was some extra explanation over here. All right, so therefore we are going to say that the smallest value of k is 1. All right, I'm going to erase this thing as well. So therefore we are going to say that the smallest value of k is 1. This is supposed to be our final answer. So in these type of questions, we always consider the x coordinate of the turning point of the quadratic graph. So this was basically the question number 34 of the handout. which is May, June 2018, paper 1, variant 1, question number 9. Alright, so now let's move on to the next question. The next question is handout question number 36, which is May, June 2018, paper 1, variant 2, question number 7. So the question says that the function f is defined by fx is equals to 7 minus 2x square minus 12x for x can take any real values, meaning there is no restriction on the domain of this function. So part 1 requirement is to express this expanded form 7 minus 2x square minus 12x in the completing square form, which is a minus 2 times x plus b whole square, where a and b are constants. Okay, so we have an expanded form which is in the form of ax square plus bx plus c. We are going to convert this into a completing square form, which is a times x plus b over 2a whole squared plus 4ac minus b square divided by 4a. This is basically the formula for converting this expanded form into a completing square form. So what we can do, we can rearrange the terms in this form: minus 2x square minus 12x and then plus 7. So we can identify that a is minus 2, b is minus 12, and c is equals to 7. So therefore I'm going to use this formula over here. Okay, so minus 2 times what? X plus minus 12 over 2 times minus 2 whole squared, and then plus 4ac minus b square over 4a. So 4 times minus 2 times 7 minus minus 12 whole squared, and then completely divided by 4 times minus 2. So minus 2 multiplied by what? X plus this will be minus 12 divided by minus 4, which is supposed to be positive 3. So x plus 3 inside the bracket, and this is whole squared. And then we are going to evaluate this complete term 4ac minus b square over 4a. So 4 times minus 2 times 7 minus 144, and then divided by minus 8. So this is positive 25. All right. So what we can do, we can rearrange this into this form: a minus 2 times x plus b whole square, which means 25 minus 2 times x plus 3 whole square. All right, so if we now make a comparison with this form, the completing square form, so a is 25 and b is 3. All right, it's not important to write a and b over here in your answer. The most important thing is this completing square form. So here was the answer for part 1. The completing square form is this 25 minus 2 times x plus 3 whole squared. So now let's move on to part 2. Part 2 says that state the coordinates of the stationary point on the curve y is equals to fx. Okay, meaning the turning point of the quadratic graph. The stationary point of the quadratic graph is the turning point of the quadratic graph. Turning point of the quadratic graph, or you can also say the vertex coordinates. Vertex coordinates, or the stationary point of the quadratic graph. These three terms mean the same. So we have achieved the completing square form. Okay, so whatever is inside the bracket, this will be equated with 0. Okay, so x plus 3 is basically equated with 0. So x is equals to minus 3, and y is equated with this constant 25. Okay, so therefore we can say that minus 3 comma 25 is the turning point of the quadratic graph, which is the stationary point of this graph of fx. Okay, the stationary point of this quadratic graph. All right, if you have a completing square form in this form, that y is equals to a multiplied by x minus h whole squared plus k. Okay, so if we want to find the coordinates of the turning point, so whatever is inside the bracket, meaning x minus h, this x minus h is equated with 0. So x is equals to h and y is equals to k. Therefore, h comma k is the turning point of the quadratic graph. Okay, and if the coefficient of x square, meaning a, is positive, so we say that turning point is minimum. And if the coefficient of x square, meaning a, is negative, so therefore we say that turning point is maximum. Okay, so here I've discussed some concept behind this. All right, for those students who don't know this particular concept. So our answer is -3 comma 25. So this was some detailed explanation over here. So here we have the answer for part 2. All right, so now let's move on to part 3. It says that the function g is defined by gx is 7 minus 2x square minus 12x, meaning the same expression, but the domain is restricted that x is greater than or equals to k. Part 3 says that state the smallest value of k for which g has an inverse. Okay, so the smallest value of k would be the x coordinate of the turning point. As we have already seen that -3 comma 25 is the turning point of the quadratic graph, the quadratic function which was given to us as fx. However, the fx domain was not restricted. The only difference is that it has become gx function and the domain has been restricted to x is greater than or equals to k. So we need to state the smallest value of k for which g has an inverse. So means that the quadratic graph will be restricted from the x coordinate of the turning point. So as an answer for part 3, we are going to simply state that the smallest value of k is -3. The smallest value of k is -3. As simple as that. Or you can simply say k is greater than or equals to -3. So which essentially means the smallest value of k. So the x coordinate of the turning point is -3. So the smallest value of k is -3 over here. All right. And it has the same explanation which I gave the explanation in the earlier question. Okay, if I make a quadratic graph over here, as we know that -3 comma 25 is the maximum turning point of the quadratic graph. So let's say somewhere over here, -3 comma 25. Okay, and if the domain is like this, that x is greater than or equals to -3, so yes, we can say that it is a one-to-one function. Okay, and when input of the function is kept equal to 0, so what's the output? You can see 25 minus 2 times 3 square. So this is supposed to be 7. All right. So if the graph is something like this, then you can say that yes, the inverse would be possible. This will be a one-to-one function. All right. So this sketch was not required over here. For 1 mark, you just need to state the value of k, the smallest value of k for which g inverse exists. All right. So now we have part 4. For this value of k, we need to find the g inverse x function. Okay, so for part 4, I can do the working over here. I'll make a separator. All right. So gx function is basically having the same expression as fx, 7 minus 2x square minus 12x. And we have also achieved the completing square form as well in part 1. So I can say that gx is equals to 25 minus 2 times x plus 3 whole squared, and the domain is that x is greater than or equals to -3. X is greater than or equals to -3. All right, this is the domain for the function gx. Now we need to find the g inverse x function. So first thing first, we will equate y with gx. So y is equals to 25 minus 2 times x plus 3 whole squared, which means 2 times x plus 3 whole square is equals to 25 minus y. So therefore x plus 3 whole squared is equals to 25 minus y completely divided by 2. Taking square root on both sides, x plus 3 will be equals to plus minus under root of 25 minus y completely over 2. So therefore, we are going to say that x is equals to minus 3 plus minus under root of 25 minus y completely divided by 2. However, when we are going to write g inverse x in place of x and in place of y, we are going to write x. So either we will keep the positive sign or the negative sign. For that, I'll leave some space first. Okay. In place of y, I'm going to write x. And we are going to see what is the range of G inverse. So range of G inverse is basically the same thing as saying domain of Gx. Range of G inverse x would be the same thing as saying domain of Gx. And since the domain of Gx is that x is greater than or equals to minus 3. So therefore, we are going to say that the range of G inverse x is that G inverse x is greater than or equals to minus 3. So we need the outputs of G inverse x to be greater than or equals to minus 3. So obviously in minus 3, we need to add something. So addition sign will come over here. So therefore, I'm going to say that G inverse x is equals to minus 3 plus under root of 25 minus x completely over 2. All right. Either you can express your answer in this form. This is also completely fine. Or otherwise you can write your answer in this form, that under root of 25 minus x completely over 2 and then subtract 3. Okay, 3 is subtracted after the square root. Alright, this is also an equivalent form. Both forms are completely fine. Alright, so this was basically the question number 36 of the handout, May-June 2018, paper 1, variant 2, question number 7. All right, so now let's move on to the next question, which is handout question number 37, May-June 2018, paper 1, variant 3, question number 10. The question says that the one-to-one function f is defined. The one-to-one function f is defined by fx is equals to x minus 2 whole square plus 2 for the domain x is greater than or equals to c, where c is a constant. So the requirement of part 1 is to state the smallest possible value of c. Okay, so as we know the fact that in these type of questions, where we have a quadratic function, so the domain is restricted from the x coordinate of the turning point of the quadratic graph. So as we can see that the completing square form is x minus 2 whole square plus 2. So when x minus 2 is equated with 0, so x is equals to 2. This is basically the x coordinate of the turning point of the quadratic graph. So this would be the smallest possible value of c. And when the domain is like this, x is greater than or equals to 2, then the graph would be a one-to-one function. As we can see that the coordinates of the turning point are 2, 2. X is equals to 2 and this 2 is equated with y. So y is basically equals to 2. So 2, 2 is basically the least turning point of the quadratic graph, meaning the turning point of the quadratic graph is above the x-axis. Okay, so when the domain is like this, x is greater than or equals to 2, then it would be a one-to-one function and this would be the smallest possible value of c. Okay, so therefore, our answer for part 1 would be c is equals to 2. We can say that the smallest possible value of c is 2. Okay, so for 1 mark, we need to just state this. This was part A, meaning part 1. In parts 2 and 3, the value of c is now 4. Okay, and the requirement for part 2 is find an expression for f inverse x and state the domain of f inverse. Okay, so first thing first, what we want is the inverse function. Okay, so the first step is that fx is equated with y. So y is equals to fx, meaning y will be equals to x minus 2 whole square plus 2. So now in the next step, I can say that x minus 2 whole square is equals to y minus 2, meaning taking square root on both sides, x minus 2 will be equals to plus minus under root of y minus 2. So when x is made the subject, So x is equals to 2 plus minus under root of y minus 2. Now when in place of x, I'm going to write f inverse x, and in place of y, I'm going to write x. So either I would take the positive sign or the negative sign. So for that purpose, I'll leave some space. Okay. And in place of y, I'm going to write x. And now I'm going to consider the range of f inverse, since we know the fact that the range of f inverse x is basically the domain of fx. And as per the information of the question, the value of c is now 4. So the domain of fx is that x is greater than or equals to 4. Okay. For part 2 and 3, the domain for fx is that x is greater than or equals to 4. This will become the range of f inverse x. So we are going to say that f inverse x is greater than or equals to 4. So we need the outputs of f inverse x to be greater than or equals to 4. Obviously, we will choose the positive sign over here because in 2, we need to add something in order to get the outputs greater than or equals to 4. So f inverse x will be 2 plus under root of x minus 2. This is basically the f inverse x function. And now we also need to tell the domain of f inverse x function. Okay, so the domain of f inverse x is basically the range of fx. So first of all, we are going to sketch the graph of fx function for the domain x is greater than or equals to 4. As we already know that 2 comma 2 is basically the least turning point of the quadratic graph. Okay. 2 comma 2, meaning when x is 2, so y is also equals to 2. This is the least turning point of the quadratic graph. However, now the domain is that x is greater than or equals to 4. Meaning the domain of fx for part 2 and 3 is that x is greater than or equals to 4. So we need to see when x is equals to 4, what is basically the output over here. Okay, we need to see this. So we are going to evaluate the value of f4. So 4 minus 2 whole square plus 2. So 2 square 4, 4 plus 2 is 6. So output is basically 6 over here. So the graph would look something like this for the domain that x is greater than or equals to 4. All right. So now according to this sketch of the graph, I can say that the range of fx is that fx is greater than or equals to 6. Now this will become the domain for f inverse x. So therefore we are going to say that domain of f inverse x is that x is greater than or equals to 6. This is supposed to be our answer. All right. So here was a requirement for part 2. So now let's move on to part 3. Part 3 says that solve the equation f of fx is equals to 51, giving our answer in the form of a plus root b. We need to give our answer in an exact form. So here we are going to solve this part 3. Okay, so we need to solve this equation f of fx is equals to 51. Okay, so first of all, I'm going to make the composite function f of fx. So fx function is basically x minus 2 whole square plus 2. Okay, so f of fx composition means that in the fx function, the input will be fx itself. So fx minus 2 whole squared and then plus 2, which means x minus 2 whole squared plus 2 minus 2. This is whole squared and then plus 2 in the end. So this 2 and minus 2 inside is cancelled out. So x minus 2 whole square is whole squared. So this means x minus 2 whole thing is raised to the power of 4 and then plus 2. This is basically the f of fx function. So now when this is kept equals to 51, meaning f of fx is kept equals to 51. So x minus 2 whole thing raised to the power of 4 plus 2 is equals to 51. So this means that x minus 2 whole thing raised to the power of 4 is equals to 49. Okay, and we need an exact form, something like this, in the form of a plus under root of b, a plus square root of b. Okay, so there would be a specific way to solve this particular equation. X minus 2 whole thing raised to the power of 4 is equals to 49. So first, if I take a square root on both sides, I would be able to say that x minus 2 whole square is equals to plus minus 7, isn't it? Because I'm taking the square root of 49. So x minus 2 whole square will be equals to plus minus 7. So this means that either x minus 2 whole square is equals to positive 7, or you can say that x minus 2 whole square is equals to minus 7. Okay, so when x minus 2 whole square is equals to minus 7, this cannot be solved. You will have no solution for this thing. Okay, because the output of this whole square function is a negative value. So this cannot be solved. So we need this thing x minus 2 whole square is equals to positive 7, meaning x minus 2 will be equals to plus minus under root of 7, because we have taken square root on both sides. So this means that x is equals to 2 plus minus under root of 7. All right. However, we would need to consider the domain of the inner function. Since we are solving the equations which are involving composite functions, so f of fx, the inner function would be fx. And as the question says that for part 2 and 3, the value of c is 4, meaning for part 2 and 3, the domain for fx is that x is greater than or equals to 4. So the value which is greater than or equals to 4 would be acceptable. Okay, so 2 plus under root of 7, yes, this value comes out to be 4.645 and so on. Okay, so therefore, your only answer would be x is equals to 2 plus under root of 7. And the other value, which is x is equals to 2 minus root 7, this will be simply rejected because this is outside the domain of the inner function. Okay, therefore your only acceptable answer is x is equals to 2 plus under root of 7. And as per the requirement of the question, you have expressed your answer in the form of a plus root b, a plus square root of b. In this way, we have solved this. All right. So you need an answer in an exact form. All right. So x is equals to 2 plus root 7 is your only acceptable answer. And you would consider the domain of the inner function as well, because whenever we are solving equations which are involving the composite functions, we always consider the domain of the inner functions. So the inner function is fx, so the domain for fx is that x is greater than or equals to 4. All right. And other thing is that after this step, you would have an alternative approach, something like this. If x minus 2 whole thing raised to the power of 4 is equals to 49. Okay, so if I take power 1/4 on both sides, meaning the fourth root on both sides, so I can say that x minus 2 would be equals to plus minus fourth root of 49. Okay, because this 4 is basically an even number. So let's say if I have x cube is equals to 8. So x would be equals to cube root of 8, meaning x would be equals to 2 only. But let's say if I have something x raised to the power of 4 is equals to 16. So this means that x is equals to plus minus fourth root of 16. X is equals to plus minus 2. Because 2 raised to the power of 4 is also 16 and minus 2 whole thing raised to the power of 4 is also 16. So here basically the power is an even number. So we would have plus minus both. All right. But we need an answer in a specific form a plus root b. Now when root b is over here, which means the square root of b. We need a square root of b. We don't need fourth root of b. Okay. So in order to make this thing possible, first of all, after this particular step, we have two conditions. One is that x minus 2 is equals to fourth root of 49, and the other one is x minus 2 is equals to minus fourth root of 49, isn't it? Now I need to make this thing, you know, in the form of a square root. I need an answer in the form of a plus root b. Now fourth root of 49 means that 49 is raised to the power of 1 over 4. Now in place of 49, I can write 7 square. So 7 square is raised to the power of 1 over 4, meaning 7 is raised to the power of half. Now 7 is raised to the power of half means under root of 7. So I can say that this is x minus 2 is equals to under root of 7. And therefore x is equals to 2 plus under root of 7. Okay. And in the same way, I'm going to say that, the fourth root of 49 is under root of 7. So I'm going to say that x minus 2 is equals to minus sign multiplied by under root of 7. So x is equals to 2 minus under root of 7. But this value, x is equals to 2 minus root 7, is not within the domain of the inner function fx, because the domain of the inner function fx is that x is greater than or equals to 4. So this will be simply rejected. Okay. So we need our answers which are greater than or equals to 4. So our only acceptable answer would be x is equals to 2 plus root 7. I hope this thing is clear. Okay, this was basically an alternative approach. We had converted this fourth root of 49 in the form of a square root because we need our answer in a particular form, a plus square root of b. Okay. So this was basically the question number 37 of the handout, May-June 2018, paper 1, variant 3, question number 10. So now moving on to the last question of this recording. This is question number 39, October-November 2018, paper 1, variant 3, question number 11. So the question says that express 2x square minus 12x plus 11 in the form of a times x plus b whole square plus c, where a, b, and c are constants. Okay, so we need to convert this into a completing square form. So 2x square minus 12x plus 11, this is the general form of the quadratic expression, ax square plus bx plus c, and we need to convert this into a completing square form, and the formula is a multiplied by x plus b over 2a whole squared plus 4ac minus b squared divided by 4a. So a is 2, b is minus 12, and c is 11. So 2 times x plus minus 12 over 2 times 2 whole squared, and then plus 4 into 2 into 11 minus b square. In place of b, I'm going to write minus 12. So minus 12 whole square is subtracted and then divided by 4 times 2. So far we have achieved this thing. So this means that 2 multiplied by x plus, this is minus 12 over 4, meaning minus 3. So x minus 3 whole square, and then 4 into 2 into 11, subtract 144, and then divide by 8. So this is minus 7. So this is basically the completing square form which we are looking for. 2 times x minus 3 whole square minus 7. This is supposed to be our answer to part 1. So now moving on to the next part. First, we have some information that function f is defined by fx is equals to 2x square minus 12x plus 11 for the domain x is less than or equals to k. The requirement of part 2 is to state the largest value of the constant k for which f is a one-to-one function. Okay, so completing a square form we have achieved. So x coordinate of the turning point is x is equals to 3, because when x minus 3 is equated with 0, so x will be equals to 3. This will give you the x coordinate of the turning point of the quadratic graph. So if the domain was like this, x is less than or equals to 3, then we would say that it is a one-to-one function as well, and also this is the largest value of k for which f is a one-to-one function. Okay, so as we can see that, the turning point, the coordinates of the turning point are 3 comma minus 7, and since the coefficient of x square is positive, so this is the least turning point quadratic graph. Okay, so if I make a sketch over here, so x is equals to 3 and y is equals to minus 7, so this is the least turning point of the quadratic graph. And when input of the function is x is equal to 0, so output would be 11, 2 times 9 and then minus 7. So the graph, would look something like this. Okay. So if the domain was like this, x is less than or equals to 3. So it is a one-to-one function as well, and this is the largest value of k as well. So let's say if the domain was like this, that x is maximum 2. So 2 times 2 minus 3 whole square and then subtract 7, this will give you minus 5. Okay, so if the domain was something like this, that x is less than or equals to 2, okay, so the graph would look something like this, which I am marking with green pen. So we would say that yes, this is a one-to-one function. However, this is not the greatest value of k. Okay, so I believe I've given enough sufficient detail regarding solving these type of questions in earlier questions as well. And here I've also given some detailed explanation further. So our answer would be the largest value of k would be equals to 3. So therefore we are going to say that the largest value of k is 3. This is supposed to be our answer. And all of this explanation is extra detail which I have given repeated times earlier as well. Okay, so the answer we have achieved for part 2. Now coming on to the next part. Part 3 says that for this value of k, find an expression for f inverse x and state the domain of f inverse. Okay, so I'm going to erase this thing over here. All right, and I'm going to solve part 3 over here. I'm going to make a separator. So for part 3, we need to find the f inverse x function, and for this value of k, meaning now the domain for fx function is that x is less than or equals to 3. Okay, so first thing first, fx will be equated with y, so y is equals to fx, meaning y is equals to, the completing square form is 2 times x minus 3 whole square and then minus 7. So therefore I'm going to say that y plus 7 is equals to 2 times x minus 3 whole squared. So x minus 3 whole square is equals to y plus 7 completely divided by 2. So taking square root on both sides, x minus 3 will be equals to plus minus under root of y plus 7 completely divided by 2. Therefore, x is equals to 3 plus minus under root of y plus 7 completely over 2. So now in place of x, when I'm going to write f inverse x, and in place of y, I'm going to write x. So either we will choose the plus sign or the minus sign. And for that purpose, I'm going to leave some space over here. Okay, and then we are going to see what is the range of f inverse x. Okay, as we know the fact that the range of f inverse x is basically the domain of fx. Okay, and the domain of fx is that x is less than or equals to 3. This is the domain of fx. So this will become the range of f inverse x, meaning we are going to say that f inverse x is less than or equals to 3. We are going to say that f inverse x is less than or equals to 3. So we need the outputs of f inverse x to be either equals to 3 or below it. So from 3 we have to subtract something, right? So the minus sign will come over here. So therefore f inverse x is equals to 3 minus under root of x plus 7 completely over 2. Okay, this is the f inverse x function. And now we also need to state the the domain of f inverse, and for that purpose we are going to observe the range of fx. Okay, so domain of f inverse x is basically the range of fx. So we already sketched the graph in earlier part in my earlier working. I'm going to sketch it again over here. No issues. So as we saw that, the least turning point of the quadratic graph was 3 comma minus 7. Okay, x is equals to 3 and y is equals to minus 7. This was the least turning point of the quadratic graph, and the graph would look something like this. Okay, we saw that when x was 0, output was 11. So what we can say that the range of fx is that fx is greater than or equals to minus 7. as simple as that. This is the range of fx function. Fx is greater than or equals to -7. Now this will become the domain of f inverse x. Therefore, domain of f inverse x would be x is greater than or equals to -7. This is supposed to be your domain for f inverse x function. All right. So this was the solution for part 3. So now let's move on to part 4. It says that the function g is defined by gx is equals to x plus 3, meaning gx is a linear function for the domain x is less than or equals to p. Part 4 says that with k now taking the value 1, find the largest value of the constant p which allows the composite function fg to be formed, and find an expression for f of gx whenever this composite function exists. So I'm going to bring the picture of the question on the next page. Okay. So it says that with k now taking the value 1. Okay, so k is now 1, which means that fx is equals to 2x square minus 12x plus 11 for the domain x is less than or equals to 1. Okay, because k is equals to 1. All right. And what we need to find, we need to find the greatest value of the constant p, which allows the composite function fg to be formed. Okay, when fg exists, the condition for fg to exist, okay, as you have already studied and I've discussed this concept in my earlier videos as well, that the range of g must be contained within the domain of f. This is basically the rule for the composite function fg to exist. The range of g must be contained within the domain of f. Okay, so now let's observe this gx function. Gx is basically a linear function which is x plus 3 for the domain x is less than or equals to p. Okay, so now I don't know the value of p. I need to find the value of p. Let's say p is unknown. So let's make a sketch for this linear function gx. Okay, gx is basically x plus 3, meaning the graph would be like an upward sloping line having a gradient of 1 and the y-intercept 3. So let's say if there was not any restriction on the gx function, the graph would look something like this, that the y-intercept would be 3, okay, and the gradient would be equals to 1, and the x-intercept would be -3. All right. So right now I don't know the value of p, but let's say p is somewhere over here. Let's say p is somewhere over here. So I'm going to, restrict this graph for the domain that x is less than or equals to p. So I'm going to erase the extra part of the graph now. And according to my domain, the graph would look something like this. So when x is equals to p, the output would be p plus 3, isn't it? Because gp would be p plus 3. So this would be the output. So now when the domain of gx is that x is less than or equals to p, so the range of the gx function, the range of gx function would be something like this, that gx is less than or equals to p plus 3. Make sense or not? According to the sketch of this graph. As you know that in order to find the range of any function, always helpful to sketch the graph. So the range of gx is that gx is less than or equals to p plus 3. Okay, so the range of g must be contained within the domain of f. Now this range of g will become the domain for f. Okay, and the domain for f is that x is less than or equals to k, and specifically for this part for k is equals to 1. So I'm going to say that the domain for fx is that x is less than or equals to 1, and the range of g will become the domain for f, meaning the domain for f will now become x is less than or equals to p plus 3, isn't it? Make sense or not? So if we just make a comparison, we can say that P plus 3 is equals to 1, meaning P will be equals to 1 minus 3, therefore P is equals to minus 2. So when P is equals to minus 2, we can say that the range of G is contained within the domain of F. This is the largest value of the constant P. We have just made a comparison of these two inequalities over here. The range of G will become the domain for F. Okay, this is the largest value of P. Okay, and now what we need to do, we need to find F of Gx as well. Okay, and as I mentioned this earlier that P was unknown initially, so I kept it over here a positive value. However, now since we have known the actual value of P, which is minus 2, so actually, the Gx graph would look something like this, that the value of P is minus 2. So when value of P is minus 2, so output, this will be equals to 1. And the x-intercept of the graph would be minus 3. So now, the graph would look something like this for the gx function. Because the actual value of P now we have found. Initially, that value of P was unknown. And this is basically the greatest value of P for which the composite function fg exists. Okay. So here was one part of this requirement of this part 4. And now what we need to do, we need to find the f of gx function. Okay, so that is very simple now. So fx function is basically the completing square form which we achieved earlier, 2 times x minus 3 whole square minus 7. So I'm going to use this. So 2 times x minus 3 whole square and then minus 7. And now input of this f function is g itself. So this becomes 2 times gx minus 3 whole square minus 7. And in place of g, we are, going to write the linear function x plus 3. So 2 times x plus 3 minus 3 whole square and then minus 7. So this becomes, something like this, that 3 and minus 3 are cancelled out. So 2x square minus 7. So therefore, f of gx, the composite function is that 2x square minus 7. This is supposed to be your answer. All right. So this was the solution for, part 4. All right. So this was question number 39 of the handout. October-November 2018, paper 1, variant 3, question number 11. So this was basically the last question of this particular video. In this video, I've discussed 4 questions. In earlier video, I've discussed 3 questions. Inshallah, I'll be uploading more content. So stay tuned to my channel. Thanks for watching. If you like my content, do consider subscribing it and sharing it with your friends. See you in my next video. Assalamu alaikum. And students, those who have any queries related to, any particular explanation in my video, if they do not understand any particular thing and they want me to repeat it for them, so always feel free to contact me on my WhatsApp number. Okay. Or you can send me a DM as well on my Instagram as well. However, it's recommended to use WhatsApp because I would be able to, comfortably explain you the queries in a form of voice note as well. And if any further detail is required, mostly I use WhatsApp, highly active over there. So if any student has any queries, so I'm always available on WhatsApp as soon as I'm free because I have a very busy schedule throughout the day. As soon as I'm free, I would be able to respond to your queries. Assalamu alaikum.